Okay, welcome back, folks. We've talked a little bit about thermal properties of that the Drude model predicts, and we also talked a little bit about the thermoelectric effect. Now we'd like to shift gears and look at what the Drude model has to say about optical properties of metals. Okay, so optical properties of metals. According to sort of the classical picture, the Drude model representing the classical picture of electrons in a metal. In our textbook, you can read an engineering version of this treatment in chapter 11. Okay, so before we had this formula, m dv dt plus gamma times v is equal to E times capital E. This is from the perspective of a particular conduction electron. So this m here, for instance, refers to the mass of an electron. Okay, so then let's talk a little bit about this E. Before, it was a static electric field due to a voltage that was applied. We apply a voltage across a metal wire, and then a static current develops in response to that. Now, since we're talking about optical properties, this electric field will not be due to an applied voltage. It will be provided to us by the electromagnetic wave passing through. Okay, and so this electric field here will be time dependent and will have this kind of time dependence. So sinusoidal time dependence. There's not going to be a spatial dependence that I'm including, so it's not e to the I kx minus omega t, because here I'm still assuming that the wavelength of light is large compared to the interatomic spacing. So on that atomic scale, the wavelength is going to be very large, and so we don't have to include the spatial component. So it's sinusoidal in time and uniform in space. Okay, so in reality, of course, we have to keep in the back of our mind that we are really talking about the real part of that formula, the real part of E naught e to the I minus I omega t, which is just E naught times the cosine of omega t. Okay, so we want to use the Euler notation, but in the back of our mind, we also realize that in the end, we're only going to be attributing the real part to a physical quantity. All right, so let's look for a steady state solution to that differential equation of the form v of t is equal to, again, the real part of this Euler expression. All right, so why are we looking for solutions of this form? Okay, so we now have an oscillating electric field, okay, impinging upon the metal. We would expect then the electrons that are subject to that electric field to also oscillate back and forth. It can no longer be just sitting there statically or moving statically. There's going to be an oscillation in the velocity due to the oscillating field. Okay, so that makes sense. Now, what we're going to do here is we're going to plug that ansatz back into the differential equation. So put that into there, okay? And what you see then is we have to here take a derivative. Well, this is why we're using this Euler form, right? It's because it's very easy to take a derivative of this. All that happens is we bring out a minus I out front when we differentiate. And so that's exactly what happens here. In the first term, we get an additional term, multiplicative term of minus I omega. Okay, and the rest basically stays the same. Okay, and so let's combine that with what we know, the relationship between velocity and current density to be, namely J is equal to NeV. And so if we insert that into the formula above, we get this expression now. So we just cast it in terms of J. that introduces another factor of n times e over here. And so overall now we're left with ne squared times capital E. Okay. Now you can solve that for j. It's just algebra, right? And we get this expression for j. Okay, good. Now before we had that j was equal to sigma times e, and that's just Ohm's law, right? This is just Ohm's law. And so now we want to basically compare what we got up here to what we know to be Ohm's law. And that then forces this sigma, that conductivity, to have this form. Namely, it's just what appears here in the parentheses. Okay, and so that is one thing you have to realize is that there is this complex I here, this imaginary I here. So this is going to be a complex number. Okay, but before we get to that, we also remember that from the Drude model, we get that sigma of 0 here, indicating that it's the static situation. Omega is equal to 0, no fluctuation at all. We got this formula, ne squared tau over m, and so let's combine that, these two expressions. Okay, we're already getting an ne squared into the numerator. There's an ne squared here as well. Okay, I want to get this sigma 0 into that expression, and it's not very hard. What we get is that we get sigma 0 times m over tau, okay, all over that previous denominator, and we can bring this factor into the denominator, and we get something like that. Now, something nice happens here, because this gamma times tau, or tau times gamma, is nothing other than m. This was on a previous video where we derived that. So that makes it particularly nice, because then this first term here, okay, tau times gamma over m, is going to just turn into 1. Okay, and so that becomes 1, and we get this final result here, that the conductivity at a frequency omega is equal to the static conductivity sigma 0 over this denominator that's complex. Now, one thing that we might want to do is to write this expression in terms of the standard form for a complex number, namely the sum of a real part and an imaginary part. So I kind of would like to write this sigma up there in the purple frame, that sigma. I'd like to write it in, I'd like to separate out the real part from the imaginary part. I'd like to write it as sigma prime plus I times sigma double prime. Okay, so how do we do that? Okay, we start with what we just had, okay, and then conjugate the denominator. In other words, multiply top and bottom by the complex conjugate of the denominator. That turns then the denominator into a real number, right? So what we're going to do here is we're going to multiply top and bottom by 1 plus I times omega times tau. Okay, we can do that, of course. And then the denominator becomes simply just 1 plus quantity omega tau squared. So it is now a real denominator. And in the numerator, we get the real in the complex, the real in the imaginary part. All right, so now it's very easy to see what sigma prime is, namely it's just this part here, right? And similarly, sigma double prime is just this part here. Okay, so the prime and double prime obviously are not referring to derivatives of any kind. It's just a placeholder for real and imaginary part. All right, so here is the summary. We have the real part and the imaginary part, and then the entire conductivity is given by real part plus I times imaginary part. Okay, so these are very nice and compact formulas. But the question is, what do they do for us? Okay, what is this all good for? Let's interpret these formulas. All right, so first, I want to remind you of what conductivity even measures. So here again, it is good to go back to Ohm's law. Namely, the sigma gives you the relationship between the electric field and the current density. Okay, and so let's say we say that the electric field varies sinusoidally. Okay, so it's proportional here, let's say, to e to the minus I omega t, and this j is also going to be proportional to that same factor. They're both basically sinusoidal. And so now when you look at this sigma, the constant of proportionality, if it is real, if it's a real number, we see then that the j will be entirely in phase with the e. Okay, and so that part, that real part of sigma, will give us that part of j that is in phase with the electric field, E. Right, because if I just multiply E by some real constant, say 2 or something, well, I would still need some units there too, but then, well, I'm going to get 2 times e to the I minus I omega t, right? And so we're still completely in phase. 2 times the cosine is obviously in phase with the cosine. All right, so the more interesting question really is, what does the imaginary part of sigma do for us? So the sigma double prime. Well, here we're not multiplying by 2, we would be multiplying by I, right? An imaginary number. And so we'd have this combination I times e to the minus I omega t. What does that give us? Well, one thing to remember here is this I can be written in polar form. Okay, so in polar form, it just looks like e to the I times pi over 2. So e to the I times pi over 2 is identically I. It's a nice identity there. And so I'm replacing that. Now I have sort of this product of 2 exponentials. Well, I can add the exponents together. And so what I'm ending up with then is e to the minus I quantity omega t minus pi over 2. And so now we see that if E, capital E, the electric field, is proportional to e to the minus I omega t, then J would be proportional to this thing here. Okay, and the two are no longer in phase. And as a matter of fact, they're out of phase exactly by pi over 2. So we get that the current is 90 degrees out of phase with the electric field. So that's what the imaginary part of sigma does for us. It gives me that component of the current that is 90 degrees out of phase with the electric field. Okay, but for now, for a moment, let's come back to the real part of sigma, namely sigma prime. All right. So we said it already said that part creates a current that is in phase with the electric field, current density. Okay, and so that current, I'm going to claim, produces resistive heating of the metal. Why am I claiming that? Well, let's think about work and how it is defined, right? In introductory physics, we know that work is force times displacement, or the integral f dx. But we can also write it in terms of the velocity, right? The integral f times v with respect to time. All right. So the force, though, well, okay. So they're all time-dependent quantities here. Force is a function of time. The velocity is a function of time. And so here, I'm just then inserting what we know the force to be. That's E times the electric field. And the velocity is related to the current density, right? And so I can write this integral as 1 over the number density integral E times J over time. Okay. Now, if E and J are in phase, like for instance, the electric field is E naught times the cosine of omega t, and the current density is J naught times cosine of omega t. Well, then if I plug that back into the integral, the work would just be proportional to this integral of cosine squared, because we get the cosine term from both the E and the J contribution, right? And so, but then the power is work over time, and we can basically get this integral over one period. Okay, that should be 1/2, and we get this nice formula for power, which is larger than 0. It's positive. Okay, so we have a positive power, and so that power has to be dissipated inside of the metal, and it's dissipated resistively. Okay, that's really an important point here, and we almost have to pause to let it sink in. So this power that electromagnetic waves impart on the electrons is positive, right? And so the electrons have to, in steady state, have to dissipate that power. Okay, and so they bump into ions, for instance, and so on, right? And so it's resistive dissipation that we're talking about here. So the next thing that we want to talk about is the out of phase component that comes about due to sigma double prime. Okay, what does it do? Well, I can do a similar analysis here, and we would get an integral that is cosine omega t times the sine of omega t integrated over one period, right? Because we have the electric field proportional to, say, cosine of omega t, but J is pi over 2 out of phase, and so that gives me the sine of omega t, right? And so now I don't get cosine squared, I'm going to get this combination cosine times sine integrated over time, and we know that that's going to be 0. And so the sigma double prime does not contribute to a power transfer from the electromagnetic wave to the electrons in the metal. And so there is no power dissipation either that is associated with sigma double prime. Okay, so that's an important piece of it to keep in mind. Now, let's go back to the formulas we just derived earlier. Okay, and now let's look at these formulas with in the limit of omega tau, the product here, being much less than 1. Let's see what happens in that small frequency limit. Okay, if you look back at the formulas, you see that, double prime, sigma double prime, it then goes to 0 because it has omega tau in the numerator. So that's easy. And actually, the other one is just as easy. The sigma prime just approaches the sigma naught. Okay, and so it's very simple there. We don't get an out of phase component at all. The electrons respond to the electric field in phase. They are in phase. Their motion is completely in phase with the electric field. Okay, and so in this limit where omega is just much less than 1 over tau, we have basically resistive currents and therefore also energy dissipation. And we have to remember that the source of the energy, sort of the driver of the system, is this time-varying electric field that comes from the electromagnetic wave. We're making use of the electric field and the oscillating electric field inside of this electromagnetic wave. We're not concerned with the magnetic field part of the electromagnetic wave. We're just picking out the electric field of the electromagnetic wave. And so the upshot then is, of course, that the electromagnetic wave will dissipate or damp out inside of the metal, right, in this limit of omega just being much less than 1 over tau. we're going to get that dissipation of the electromagnetic wave inside of the metal. Okay. So this is the limit, right? The 1 over tau. But what is 1 over tau? Well, tau is the relaxation time, and we said it is on the order of 10 to the minus 14 metals across a wide range of metals. And so 1 over tau then is on the order of 10 to the 14 hertz. And so we are saying that as long as omega is less than 10 to the 14th, radians per second really should be the units here. Or we can convert that also into a lambda, a wavelength. So as long as the wavelength is larger than c over the frequency nu, or c over omega over 2 pi, okay, which, okay, I can bring the 2 pi upstairs and I can evaluate that. And when I do, I get about 9 times, wait, let me see here. Okay, so yes, forgot the times 2 here. So that actually gives us 18 roughly micrometers. So we are in the infrared here, clearly. So as long as we're in the infrared, certainly in the far infrared, then we can say that omega is much less than 1 over tau, and we should get these electromagnetic waves absorbed. Okay. So that's our first conclusion, that basically all electromagnetic radiation, starting from radio waves through microwaves up into the infrared, should simply be absorbed by the metal, right? The E&M waves are absorbed by the free electrons in the metal because they behave resistively in that limit. Okay, so just as a quick example, right, this is why a metal box, and it doesn't even have to be very thick. If you've ever noticed your microwave oven, it's pretty thin box. And moreover, the front panel, well, if you've ever looked there, it's a pretty thin metallic mesh, right? But that is enough to shield you from the pretty intense microwaves that are inside of the oven. And so the metal, it doesn't have to be very thick, basically absorbs all the microwaves. Okay. On the other hand, when the frequencies do get higher, and in particular when they get very high, such that omega is much, much larger than 1 over tau, well, then if you look at our formulas again, things will be different. Here are the formulas for sigma prime and sigma double prime. Okay, so now stare at them for a moment and see what would happen in the limit of omega times tau being much larger than 1. So this one here is the easy one, right? You just see that the denominator becomes large, and eventually then sigma prime is going to approach 0. Now, what about over here? What happens over here in the limit of omega tau being much larger than 1? Well, you can reason this through pretty quickly as well. You can just realize that in the denominator is omega tau squared is going to dominate the 1. You can almost forget about the 1, and you're approaching sigma naught times omega tau over omega tau squared. Okay, and so that is sigma naught over omega tau. And so that should also go to 0, right? So they should both approach 0, but of course, sigma prime is going to approach 0 much, much more quickly than sigma double prime. And the ratio of sigma prime to sigma double prime goes to 0. That's all a way of saying that sigma double prime will dominate the sigma prime in this limit. Okay, so sigma double prime will just be much larger than sigma prime. They're both going to be small, but the double prime is going to dominate. That's it. And so in this limit here, we can say that the electrons act not resistively, but inductively. There's going to be this pi over 2 phase lag, or the 90 degrees phase difference between the electric field and the current density. Okay, this is why we call it inductive. This is exactly what happens when you induce a current using a changing magnetic field, for instance. Yeah. So, so here we should see that no energy would be absorbed, and the electromagnetic wave should pass through the metal without diminishing in amplitude. Okay, and then to summarize, we would say that on a lambda axis, right, where we have maybe long wavelengths to the right of, say, 20 micrometers or micrometers. So when we're in the far infrared here, then all of that stuff should just be absorbed. We said that. And then over here, for short wavelengths, we should get transmission through the metal. We don't know exactly where that onset is going to be, but wherever it is, this region should be, short wavelength should be transparent. But certainly up here, everything should be opaque. And the question is, where is that crossover there, and what happens in between? And so in order to answer those two questions, we really need a more detailed approach. Okay, and so we can't get away from, get away from Maxwell equations, which are sort of the ultimate equations to describe the electromagnetic wave. So far, we've skirted that because it gets more complicated, of course. But if we want to know more precisely what's going to happen sort of in this crossover region, or where exactly this transparent region turns on, well, then there's no way around the Maxwell equations, and we would have to then spend some more time and engage in a more detailed analysis. So that will be next time, folks. We're going to stop here for now. Thank you.